we can start the session. So our first talk is Li-Hwai Lin, giving a review talk on spatially resolved studies, probing the connection between gas and star formation in nearby galaxies.
Hello, everyone. So my name is Li-Hwai Lin from HIAA. So I'd like to thank the conference organizer for inviting me to this wonderful conferences. So today I'm going to discuss how we can use spatially resolved observation to improve our understanding about the connection between gas and star formation. So as we hear a lot this morning, that one of the key figures that describe the population of a galaxy is this star formation rate versus stellar mass plan. So you can see that the star-forming galaxies form a very tight sequence here, and below which there is a distinct population of quiescent galaxies. So this diagram leads to two outstanding questions. The first one is why there is a star-forming main sequence, why the current star formation rate of galaxies should depend on the time integral of the past star formation rate. And the second question is under what kind of condition the star formation can get quenched. So to answer this question, of course, we need to take into account the molecular gas, which is the fuel of the star formation. So here you can see that the cosmic evolution of star formation rate is very similar to the evolution of the molecular gas. So to first order, the star formation rate depends strongly on how much you can have from the molecular gas. In addition to that, the measurement of the star formation efficiency and also the gas fraction are also very important. You can see here that the gas fraction and also the star formation efficiency varies not only across the main sequence, but along the main sequence, but also across the main sequence, suggesting that the molecular gas is playing a very important role in regulating the shape of the star-forming main sequence. However, as we have already been heard a lot, that the star formation is a very complex process. So it involves the process across very different physical scales. So for example, at larger scales, the large-scale environment and the distribution of ICM and CGM both play important role in shaping the accretion rate of the gas and also impact the growth and assembly rate of the galaxies. And on the other hand, the star formation really take place within the molecular cloud, which are of typical size of parsec or tens of parsec. So the physical scale spans a wide range of the order of magnitude. So the real question is how we can use the knowledge of this microphysics happening within the molecular cloud to understand what's going on to describe the global properties of galaxies. So one of my favorite examples to showcase the power of the resolved observation is this resolved star-forming main sequence. So having the IFU observations, we can now identify the ionizing sources in small regions within the galaxies. So for example, here, if we only look at the star-forming spectrals, and we can see that the surface density of the H-alpha, or the star formation rate, is tightly correlated with the stellar mass on the KPC scales. And this sequence also extends to the global sequence, so meaning that perhaps the global main sequence is recollections of all the phenomena happening locally. However, this doesn't really answer why locally the star formation rate should depend on the local stellar mass, right? So we also have to take into account this molecular gas to fill in the picture. So we know that there's will correlate the relation between the star formation rate and the gas mass through the chemical relation. And we just talk about this star forming main sequence here. So the question is whether there is also a relation between the stellar mass and the gas mass. And if there is such relation, to what order this sequence is important and which one is more fundamental over the other. So I also want to highlight that having the resolved observation to constrain this star formation efficiency and the gas fraction is also very useful in terms of constraining what's the main quenching mechanism. And this is because for external processes, for example, the ramp pressure stripping or interaction with another galaxies, they can remove the gas or prevent the gas from cooling, in which case you will have a reduced star formation. And on the other hand, for some internal process, they can inject turbulence into the ISM, or they could stabilize the cloud in the disk, preventing them from collapsing, in which case you will have the reduced star formation efficiency. So comparing these two quantities will be very important to shed light on the quenching process for a given galaxy. So motivated by all these sciences, there have been a lot of programs to combine the IFU survey with the gas observations. Just to name a few here, H. Khalifa Coming and also FANS, and then also AlmaQuest. So each of them has a different spatial resolution, so that can be complementary to each other. So I'm heavily involved in this AlmaQuest survey, which target the 46 manga selected galaxies. So we can study the gas content across a wide range of the galaxy population. So with the AlmaQuest, we can simultaneously measure the stellar mass, star formation rate, and gas mass with the matched spatial with the matched resolution. So Professor Kennicott kindly showed this work the other day. So what we see here is the three-dimensional distribution on the three quantities that I just mentioned, the stellar mass, star formation rate, and gas mass surface density. So these are only for star-forming speckles in star-forming galaxies. So what you can see here is that basically they follow a cylinder structure, and as a result, when they project them into two-dimensional plane, each of them also form a nice sequence. So here we have the SK relation, and we also have the star-forming main sequence, and you can also notice that there is a good correlation between the gas surface density and the stellar mass surface density, which we call it the molecular gas main sequence. And this has also been carried out through different surveys, and basically we all found a very similar trend. So with these three scaling relation in hand, then now we can ask which one or which two are more fundamental over the other. So based on several different analyses, our conclusion is that the SK relation and the molecular gas main sequence are tighter and also more physically driven, such that the combination of these two relations can naturally lead to the star-forming main sequence. And so we know that the SK relation is because the star formation rate are formed in the molecular cloud, so they have a tight relation. And the fact that the star formation, the stellar mass also traces the gas mass is because in the local universe, we know that the stellar particles set the potential of the disk. So the gas distribution are very similar to what is distributed in the stellar particles. So they will also have a good correlation. So I would argue that these two are more physically driven, and the star-forming main sequence is just a natural outcome from these two relations. So we can take a step further to ask, then what happens to galaxies under quenching? The 3D relations I showed earlier is only for main sequence galaxies. But we know that for galaxies that are under transition, they have suppressed star formation rate. So either they have to have reduced gas or they have reduced star formation efficiency. So before going to the scaling relations, I want to mention that it's worth noting that for Green Valley galaxies, they tend to have less star-forming regions and more retired speckles. So in the later part of this talk, I will separate these two regions. So here I'm showing you again the 3D relation for both main sequence galaxies, which are shown in blue, and the green dots are for the Green Valley galaxies. So I know it's a bit confusing to look at this, but the bottom line is that you can see that the green points are offset from the blue points. So we can take a closer look by looking at the two-dimensional relation. So here, the left panels are for the SK relation. The right panels are for the molecular gas main sequence. And all the dots, the top panels are for main sequence galaxies, and the data points in the bottom panels are for Green Valley galaxies. The red panels are for retired regions. The green or the white panels are for the star-forming speckles. So here I just want you to focus one fact that when we compare the main sequence and the Green Valley galaxies, in star-forming speckles, you see that the Green Valley galaxies form a different relations compared to the main sequence galaxies. So they have a lower amplitude of the star formation rate for a given stellar mass. And on the other hand, for the molecular gas main sequence, we see a very similar trend that the Green Valley galaxy is offset from the relation formed by the main sequence galaxies. So this means that for Green Valley galaxies, the quenching process is probably globally because it not only increase the regions of the retired region, but also it suppress the star formation even in the star forming regions. So another way to describe this is that we can look at the distribution of SFE and also the gas fraction, and we can compare between main sequence and Green Valley galaxies. So overall, we found that the Green Valley galaxies show both the lower SFE and also lower gas fraction compared to the main sequence galaxies. So in other words, the Green Valley galaxies have maybe a mixture of process going on that leads to both the lower gas fraction and the lower SFE. And so those results are all from the MANGA and ALMA quasar survey at low redshift. So how about the situation at high redshift? So the challenging for doing this at high redshift is that it's difficult to get a KPC scale observation simultaneous for both star formation rate, stellar mass, and gas measurement. So what I did here is that I took the global measurement divided by the total area. So this is actually a global surface density. And then I took some sample from a nice paper by Tadaki et al., which have a redshift 2 sample, and they are both star-forming galaxies, and they have the gas measurement from ALMA CO, also the star formation rate from ALMA dust continuum. So when I calculate the surface density for these three quantities, what I found is that for the SK relation, the trend formed by local Alma quasar sample can also be extended to high redshift with less scatter, but the situation become more dispersed when you look at the molecular gas mass sequence. So you see that the scatter at redshift 2 seems to be larger. Of course, this is only small sample, but I think there is, this is kind of expected because if you remember, the molecular gas mass sequence locally is because the stellar particles set the gravitational potential, right? But at redshift 2, the gas is much more abundant, so it's no longer true that the stellar mass dominate the mass budget. So to some sense that the molecular gas mass sequence might break down when you move to higher and higher redshift. So apparently we need more sample, but I also want to fill in the gap between redshift 0 and 2, and I believe there should be some redshift 1 sample that are suitable for this purpose. So if anyone knows and want to contribute, please talk to me. So as a result, when you combine this SK relation and the molecular gas mass sequence, you see that the star-forming mass sequence using the surface density quantities also become worse at least in these cases. So now I want to move to the dense gas in Green Valley galaxies. I mentioned that using CO, the gas fraction and star formation efficiency are lower in Green Valley galaxies. But keeping in mind that the critical density of CO is only 10 to the third per cubic center, so it traces not only the dense gas but also the diffuse gas, which are not relevant for star formation. So it is possible that the low SFE measured in CO is due to either the lower dense gas fraction or because of the lower dense gas SFE. So we want to distinguish these two scenarios by having the dense gas observations in our sample. So that's why we follow up some of the galaxies with HCN and HCO+, which are thought to be a good dense gas tracers. So we have 2 main sequence galaxies and also 3 Green Valley galaxies. As you can see that both the HCN and HCO+ are well detected in all cases, meaning that these Green Valley galaxies might not be deficit in the dense gas. So now we can also look at the dense gas SK relations. So here, the blue points represent the main sequence galaxies, and the green points are for the Green Valley galaxies. So we already know from earlier slides that the Green Valley galaxies are offset from the main sequence galaxies when using CO, but now the same trend also present for the HCN and HCO+. So this means that the star formation efficiency in dense gas for Green Valley galaxies is also lower compared to the main sequence galaxies. So of course the question is why these Green Valley galaxies have the dense gas but they are not forming stars. Okay, so coming back to the 2 scenarios that I want to test. First, whether the low SFE in CO is because of a low dense gas fraction or not. So our answer is no, because when we look at the distribution of the dense gas fraction in either HCN or HCO+, you can see that the Green Valley galaxies and the main sequence galaxies distribution are very similar to each other's. But on the other hand, when we look at the dense gas SFE, you see that they both correlate very well with the CO-based SFE. And the reason the Green Valley galaxies have low CO SFE is primarily driven by the fact that their dense gas SFE is very low. So finally, we can put the Green Valley galaxies into a broader context by comparing different populations. Most of the data points here are for the star-forming galaxies, starburst galaxies, but we also include the post-starburst galaxies here. So in terms of the global dense gas fraction, you see that the Green Valley galaxies tend to have a higher dense gas fraction compared to post-starburst galaxy, and is very similar to the main sequence galaxies. On the other hand, when we look at the global dense gas Kenika-Schmidt relation, some of the Green Valley galaxies, some of the post-starburst galaxies follow the same trend as the typical star-forming populations, but some of them deviate from this relation. And for Green Valley galaxies, they are all below these relations. So what we conclude here is that perhaps the Green Valley galaxies are quenched longer, over a longer time scales, but for post-starburst galaxies, they are just recently quenched, so they might be represent different population, or they are in a different phase of transition. And the reason for the Green Valley galaxies having lower star formation is because their dense gas star formation efficiency is lower, not because they are lacking of dense gas. And it's opposite to the post-starburst galaxies. So here is my summary. So I hope I can demonstrate successfully that the resolved scaling relation are very important, and that can add a different information to understand the link between gas and the star formation. And for Green Valley galaxies, they have these scaling relations very different from the star-forming galaxies. So for some CO-bright Green Valley galaxies, they are not lacking of dense gas, but their star formation efficiency for dense gas is also low. And in the future, of course, we need to study this scaling relation for high-redshift samples as well, in order to connect their process to the ones in the local universe. And finally, I want to maybe highlight that it's also very important to understand theoretically or in the simulation why the dense gas cannot form star efficiently, and how is that compared to the observed Green Valley galaxies here. Okay, so I'll stop here and take questions. Thank you.
Questions for Li-Hwai? Yeah.
Thank you. Great talk.
Thank you.
Is there any difference in gas kinematics between Green Valley galaxies and star-forming galaxies that can explain the differences in SFE? Like Green Valley galaxies being more turbulent, and so star formation can be suppressed because of that?
Yeah, so we look at the velocity dispersion in CO between the Green Valley galaxy and the main sequence galaxies. And there's an indication that the Green Valley galaxies have systematically higher velocity dispersion, so that might suggesting that they have higher turbulence. But because the velocity dispersion are also highly correlated with the stellar mass surface density, in which case that's also higher for Green Valley galaxies. So to disentangle this effect, we need to have a larger sample in order to verify whether this is due to the turbulence or not.
Thank you.
Yeah, thanks for the nice talk. So about the comparison between redshift 0 and redshift 2 galaxies. So Tadaki et al. Sample is at the massive end of the main sequence galaxies. So it's not, I'm not sure what kind of galaxies would be ideal to do a fair comparison between redshift 0 galaxies, because I assume those are not at the massive end of the main sequence.
Yeah, so for the plot I showed earlier, for the local so here I include mainly the star-forming galaxies at redshift 0, and this redshift 2 galaxies are also star-forming galaxies. So what I'm looking for is the typical star-forming galaxy at redshift 1 for this exercise. We know that there have been a lot of measurement for starburst galaxies at redshift 1 or 2, but that would be, outlier in this relation. So I'm hoping to have a typical star-forming galaxies.
Regarding the comparison here, are you using the same tracers in order to quantify the molecular gas mass at redshift 0 and redshift, or they are different?
Sorry,
Are you using the same tracer to quantify the molecular gas mass here or not?
So for Alma Quest, it's 1 to 0, and for high redshift, I don't remember it's 3 to 2 or 2 to 1. So it's a higher transition, not 1 to 0 at all. Yeah, so there could be some uncertainty here. Yeah, but I guess my point is that the SK relation is tighter here. The trend is tighter here compared to the molecular gas mass sequence. Yeah.
Any other questions? Nope. Okay, so let's thank Li-Hwai again.
Thank you.
So our next speaker is Jing Wang, talking about the FIST survey. Clues on gas accretion and star formation from the diffuse H1 detected by FIST.
Thank you. It's my great pleasure to talk about it. I'm very happy at this conference because I see a lot of coincidence with the content I'm going to talk about today. But sometimes I don't know whether, well, I will start my talk. I'm going to talk about diffuse H1 and the data taken by FISTs. In order to be different from the FIST you heard yesterday, we put an extra S there. It's FISTs. It's a fast extended atlas of selected target survey. The sample size coincidentally the same as GASP, 114 galaxies, but our selection different totally by H1. And because there's a size-mass relation, so selection by H1 flux actually means selection by the apparent size. We just want to resolve the things we observe. We want to get the distribution and kinematics of H1 we can obtain with the fast telescope. The telescope, as you see, is a single dish. It has a relatively low resolution, 3 arcmin, and at the redshift we're targeting is roughly 5 to 10 kiloparsec. Don't be frustrated. If you have any concern about whether this resolution is good enough to deliver the science I'm going to talk about, you can ask me later. And the column density limit we reach is 5 times 10 to the 70. It's a limit previously only observable with absorption lines like the nanolimit systems. Well, but with mongoose, the story is not the same. But in the northern sky, we are still the first survey that reaching this detection limit. I will show you later. This is quite important as a reference line for interpreting some of the absorption studies. Currently, the survey progress is roughly half. We have another 3 years to go, but we already covered the most extended galaxies in the sample. Many of them actually are overlapping with the ALMA fans and other surveys. One of the reasons we conducted the survey is that the interferometry, while it well resolves nearby galaxies, they tend to miss the extended diffuse stuff. So if we use a single dish to obtain the total power H1 distribution, and if we combine it with the interferometry, we can get the high resolution and the total H1 and the low quantum density at the same time. And even better than that, if we subtract the interferometry detected dense H1 from the total H1, we get access of a newly detected phase, the diffuse H1. It can carry important information about the gas distribution. Now let's show you some of the results we obtained with the data. Here I gave two examples. The interferometry images from things and the total power from phases and the combined image. You can clearly see the envelope of low subdensity H1 surrounding the previously detected dense H1. And the radial profile H1 subdensity, of course, changed a lot. The same with another galaxy, the famous M101. And if we focus on the outer disks, the average change upshift of H1 subdensity is 0.15 to 0.4 dex. And of course, as a result, the size-mass relation changed. Thanks, Paolo, for showing this very tight relation based on 600 galaxies with imaging taken by interferometry. But now with the total power, with the correcting for the missing flux, we can say either there are more outliers in the relation or the whole relation systematically shifted. And because of this extra detection of H1, the star formation law in the outer disk, of course, also changed. This is basically similar figure Frank Bigel presented in 2008 with newly detected diffuse H1 added. We have several changes. Firstly, the scatter is larger at a given H1 subdensity. The scatter of star formation is subdensity. The scatter is larger. And the scatter and the median relation is systematically shifting downward. So the star formation is even more inefficient in outer disks than known before. And thirdly, the correlation of the scatter of the star formation, or the correlation, the dependence on stellar mass subdensity becomes much stronger, and the slope steeper is with a slope power law index 0.85. So it shows that adding back the diffuse H1 is really important to reveal the true condition for star formation in outer disks, and stellar mass subdensity play an important role there. Now I show some properties quantification about the diffuse H1. If I'm allowed to show only one figure to say something about diffuse H1, this is the figure I would show. The diffuse H1 is the total H1 after we subtracting the dense H1. As you can see, they are good rotating disks. Okay, so we can still quantify it with a sample 10 galaxies observed by both things and physics. We quantify the quantum density radial distribution. It's like the total H1 subdensity profile shifting downward. It's flat in the inner disk and drop almost exponentially in the outer disk. The velocity field is rotating, but if we compare it with the dense H1 velocity field, we get the difference. We see it's rotating in a slightly lagged way, and this is true for the whole sample. The velocity dispersion is twice larger than the dense H1. By the way, all the dense H1, they are smoothed to the faster resolution for a fair comparison. So what do they mean? They mean something about the three-dimensional distribution of the diffuse H1. Within the optical disk, the lagged rotation would suggest the diffuse H1 lies at a typical characteristic height of around 3 kpc, relatively thick disk, like the thick disk previously detected by halo gas. If we look into beyond the optical disk, if we assume the H1 to be in pressure equilibrium with the CGM, then the scale height looks like this. It drops sharply toward outer disks. That's because the velocity dispersion is relatively low actually in the outer disks. The disk is constrained by CGM pressure and become really, really thin. That's the height and the length. If we get a characteristic radius 80, that's a core density reaching 10 to the 18 per centimeter squared. It is reaching the border radius previously for magnesium 2 absorption line systems, basically, thank you, limit systems detected. Basically, that's a border radius where previous absorption line found those cool gas, and we are reaching there. Put together, this suggests a strong constraint to previous scenarios set by absorption studies. Previous absorption studies say that cool gas tend to be accreted relatively aligned with the disk with the opening angle of plus minus 30 degrees. But we say it's better than that. It's better than plus minus 30 degrees. It's a very thin plane. It is not an ocean floating clouds either. It's a connected disk. And now we're looking at how to get this diffuse H1. Why the diffuse H1 is there? We get some clues there. We found that, as Paul nicely showed in the morning, we found the fraction of diffuse H1, the mass of diffuse H1 over total H1 mass. It correlated with the interacting strengths. More interacting systems, they have more gas. So what does it mean? Does it mean the tidal interaction tend to remove gas or cause gas accretion? Because intuitively, we would think that diffuse H1 to be an intermediate phase between the warm ionized gas and the dense H1, but the transition in both directions are possible. So we get a somehow more strongly interacting systems, and we quantify the gas H1 richness as a function of level H1 being perturbed. We found a strong anti-correlation. Apparently, it suggests that with more strong tidal interaction, H1 gets depleted. But we need to remember that this is H1. Star formation and the molecular conversion also get enhanced in tidal interactions. So if we count that back, we get a corrected H1 richness. The anti-correlation disappears. There's a lack of correlation. So the anti-correlation is totally because part of the H1 is converted into molecular. And because there is a very efficient consumption of the neutral gas in order to maintain the balance here, there must be also efficient gas accretion, right? So, and theoretically, this is possible. Theoretically, the top-down turbulence cascade-driven cooling of the CGM, the bottom-up turbulent mixing-driven cooling of the CGM. Both scenarios are enhanced by tidal interactions. So basically, there are possibility of tidally driven gas accretion, and this is different from what Paulo suggested this morning, and he also suggested what our paper talk about. But basically, we are not talking about adding. When we talk about this tidally induced gas accretion, we're not talking about adding the interstellar medium of satellites to the central galaxy. We're talking about newly induced cooling from the CGM. We look into in details two systems. For one system, we found that the diffuse H1 column density throughout the disk out to large radius, they far above critical column density for thermal evaporation and for background UV ionization. So this diffuse H1, they are not only survive in the CGM, they definitely will induce cooling through thermal conduction through interaction with the CGM. So this one certainly will induce gas accretion. And if we look into the correlation of this diffuse H1 distribution with the kinematics of dense H1 detected by interferometry, we found this diffuse H1 more closely related to the kinematically warmer dense H1 than with the kinematically cooler dense H1. This confirms our expectation or speculation that diffuse H1 should serve as some intermediate phase between the CGM and the dense H1. And this test suggests the direction is from this way to that way. And the other system, differently, although most of the H1 column density are above the critical density for cosmic UV background photoionization, they are safe from the ionization, but the majority of them are below the critical column density for thermal evaporation. They should be evaporated unless some other mechanisms come in to input cooling to compensate for the loss, possibly could be due to thermal conduction. That's where we implement the turbulent mixing cooling scenario. That theory says if the interacting system has the Mach number, the sharing velocity between the cold gas and the hot gas, the Mach number is below 1, so the subsonic or transonic, there should be efficient cooling because the turbulence, the KH effect will increase the interaction between the hot gas and the cold gas, bringing them close to the peak of the cooling function around 10 to the 5 Kelvin. And we implement that model, calculate our inflow rate and cooling rate. That's roughly 1/5, 1/4 the star formation rate of the galaxy. And Paulo this morning told us the radial inflow account for roughly 1/4, 1/5 of the star formation rate. But Paulo showed, what Paulo showed is the inflow rate from the outlying dense H1, and this cooling rate can be viewed as a replenishment of the outlying dense H1 from cooling, due to cooling from the CGM. Now I come to my summary. With this fifth observation, we found the several previously known relations quantifying the behavior of outer H1 disks need to be changed. And we detect this diffuse H1, which potentially can be a useful new diagnostic for interstellar media and CGM interactions. And we found that tidal interaction may be an efficient way of producing the diffuse H1 that potentially pointing to tidally driven gas equation that can be an extra channel to close the gap between the gas consumption due to star formation rate and the lead for reservoir replenishment. Thanks.
For Jing. Paolo?
Sorry if I missed it, but did the velocity fields of these diffuse H1, do they show any evidence of inflows?
That's our next step. Before that, one of the necessary technical issues we need to address is we need to increase the resolution by comparing with the interferometry data. And that is turned out not so easy for H1. The feathering is not working in this case. I can explain later why we really need to do a joint deconvolution.
Thank you for the talk. So I have a question about the scale heights you were showing for your galaxies. Did I understand correctly? These are the scale heights, like the thickness of the H1 disk as a function of the radius normalized by the R25? Is it?
This one?
Maybe the next slide. Yes, the plot on the bottom right. Is this the scale height of the H1?
Yeah.
Okay, so because I've been working on the same sample, so I wonder, and I'm finding like the opposite trend for the scale height, like it's increasing with radius. and actually in the inner regions is like 10 times smaller. So I'm wondering if you have some comment on this. I don't know if you.
Yeah, I know your work, but correct me if I'm wrong. Maybe I missed something. Previously, people were deriving the scale height from the equilibrium, static equilibrium point of view. They tended to balance the gravity of the baryon dark matter with the pressure of the gas, right? But in this very alteration, if we do the calculation, we found the CGM pressure actually will be higher than the internal pressure, the effect of the gravity. And it is because of the squeezing of the CGM, the scale height drops toward a large radius.
So in the outer parts of the disk is the CGM that is squeezing?
Yes.
Okay, so there's a different modeling, let's say, from the dynamical equilibrium with the gas pressure in the disk, right?
Yes.
Okay. Thank you very much.
You're welcome.
Thanks, Jing. Very nice. I was wondering, can you comment about the time scale of all this? So what is the typical time scale of the interaction and the time scale for the condensation of the H1, and if this is the case of radial migration of the H1 into the disk?
That's a very good question. The condensation due to turbulent mixing, because we calculated the cooling rate, it's more like a cooling rate than time scale thing, because basically it scales with the sharing of that's the relative velocity between the cold and the hot gas. The larger that, and then the cooling rate is higher, so it really differs from place to place. Overall, it roughly some level, some fraction of the total star formation for at least the system.
Yes, I just wanted to follow up on Cecilia's question. This result on the CGM, potentially very important. Is it possible, are there any nearby edge-on galaxies that are large enough that you could test this directly, measure the scale height with radius at very large?
Thank you, Rob. You give me this chance to show the slides. We get a sample inclined the edge-on galaxies with kinematic inclination above 85 degrees, and we get some type of pseudo deconvolution to get a scale height of the diffuse H1. We measure the Z80. That's the height. That's the Z direction distance for column density to reach that level, and it's roughly 20-ish, a few tens kiloparsec. It looks a bit higher than the 1 kpc, 3 kpc I just said about the Phison galaxies, but we need to interpret it relatively carefully, because this is a projection throughout the whole disk.
We should move on to the next speaker. Let's thank Jing again.
Thank you.
And our last speaker of the day is Xuchen Lin, talking about fast ASCAP synergy, quantifying coexistent tidal and ramp pressure stripping for satellite galaxies.
Good afternoon. I'm Xuchen Li from Peking University, working with Jing, and now we would focus on effects at a much larger scale. Here we're combining the data from FAST and ASCAP Wallaby to disentangling the two kinds of invariance effects on the satellites in NGC 4636 group. And it has been well established that galaxies evolve at different speeds in different environments. And how to better quantify these different environments are a long-lasting questions. And there have been works using the projective distance from like cluster center or filament center, or use the local number density of galaxies. But actually, these are like the positional parameters. But what happens through these different environments are actually multiple different mechanisms. For example, such as the Rampersad stripping, the interaction with the hot ICM, or the gravitational interactions either between galaxies or between the large cluster and the satellites. And these different mechanisms, of course, they can be more easily studied in where one single effect is very strong. For example, this wonderful work by Jing is in Hydra cluster, which is very large and virialized, so the Rampersad stripping is dominated. But more than 30% of local galaxies are actually in group environments, which indicates that these mild environments are actually more general. And because of this environment are mild, so there could be multiple mechanisms at work simultaneously, none of which are that strong enough. In this work, we want to determine the mechanisms at work statistically and physically from this positional parameters, but to determine which mechanism is more important for certain satellites. This is our major model currently. We mainly focus the Rampersad stripping and the satellite-satellite tidal interactions. We will include more effects in the future works. And for the Rampersad stripping, we define the strength of the Rampersad stripping at the edge of the optical disc at R25, and it is the ratio between the Rampersad and the anchoring force there. And for anchoring force, we also include the self-gravity from the gas. And for the tidal interaction, this is our target galaxy. It's in blue, and it could be harassed by different perturbers like these two pink. There are two examples, and we use this tidal interaction strength model, which focus on a patch of gas which is rotating at R25 and how it would be perturbed by these perturbers, and we then sum them up. And we extend it into a profile, a function as radius for this tidal strength. And so with this, we want to decide how much gas they are strippable by tidal interaction or by Rampersad stripping. And so we define this strength at the edge of the optical disc, and we got the profile for the Rampersad stripping strength and the profile for tidal stripping strength, so we could decide the radius range, out of which these gas are strippable by Rampersad or by tidal interaction. So we define the fraction of strippable gas as this green one over the total one. And finally is we want to get the stripping time scale, which is if these conditions are the same, then after this time scale, all of this green gas will be gone. And so this is we want to get this stripping time scale. And for the calculation of strippable gas fraction, if the galaxy is resolved enough, we could use the H1 moment zero map to get a map of the which region is strippable. But most of our galaxies in this group is unresolved, so we use the median H1 profile to decide the fraction of strippable gas. And this study is enabled by a new generation of H1 surface. As Luca has just said, to get the H1 content for galaxies below the H1 main sequence is quite difficult. And with FAST, we push the detection limit of alpha, this line, down by 0.4 decades, and we can get 0.5 decs below the H1 main sequence for galaxy stellar mass of 7. And Wallaby has very large field of view, so we could, with large field of view, we can actually get from very beginning of the infalling out of 2 R200 to chase the infalling until they reach the center. And so the the first target is to disentangle these two kind of inferiority effects. And here is the size ratio between the H1 disk and the optical disk versus the Rampersad stripping strengths and the tidal strengths at the edge of optical disk, And currently we plotted all of galaxies on here. So we see there is a tentative negative correlation, but a large scatter, very large. But if we define our Rampersad stripping sample with those have more gas being strippable by Rampersad stripping, this is the RPS sample, and much tighter relation with the Rampersad stripping strengths, and vice versa for the tidal stripping sample. So after our disentangling, we find the galaxies which are mainly affected by Rampersad stripping or mainly affected by tidal stripping. And another example is the tidal reddening with the strength of tidal. And this is the total color versus the tidal strength. And these gray points, they are non-TS sample, and these large symbols, they are tidal stripping. They are mainly affected by tidal stripping. So if we only consider them, then they have a reddening with the tidal interaction. But if we consider all samples, then there is no such a trend, no such a relation. So from this, we conclude that we indeed find the galaxies which are mainly affected by which of these two kind of effects. And we find that this influence is widespread and coexistent. For Rampersad, there are 72% of them have more than 1% of gas affected by Rampersad, strippable by Rampersad, and on the right, 49% of them is affected by tidal stripping, and 80% of them in total are affected by at least one kind of stripping, and 41% of the H1 detected galaxies are affected by both kind of mechanism. So after disentangling them, now we combine these two kind of stripping effects to get the total timescale for stripping. The total strippable gas fraction is the maximum one between these two F. And to get a numerical fitting model, so we use a numerical fitting, a linear fitting for them with the gas richness and the projected distance from the group center. And this is the vertical distance from the H1 main sequence. And to get the timescale, we try to link the decrease of H1 with respect to the distance. Link this with how it loses its H1 with time. And so we assume that our target galaxy is the first time infaller into this group from R2 R200. And so we use this model to get stripping time scale. And the first term is the drop rate of the gas richness. Because if in this simple model, the distance from the group center is just a reference for the time, it's infalling time. And the second term is the stripping rate, the strippable gas over the stripping time scale. And the third term, yes, of course, it can lose its gas either from stripping or from the star formation consumption. So this is the third term. We assume a star formation efficiency of this from from X gas. And so this is, from our assumption, we focus only on the most H1 rich galaxies. And we, as a very preliminary, we use this power law model. And we focus only on top H1 rich galaxies in these 5 beams. And we MNC fitting to get this profile for most gas-rich galaxies to infall into this group as the first time infall. And this is the profile of this simple stripping timescale model. And this line is the stripping timescale estimated in the more massive Hydra. And we can see that in this group, it varies in a wide range at the edge of the group is about the Hubble time. But when we near the center, it could possibly very similar to the free fall time of the H1 gas. And compare with the Hydra value, you can see they are consistent. While we would expect that in Hydra, because it is more massive, more hot, so the ramp pressure stripping there would be more effective. It is possible that in this young group, the tidal interaction between the galaxies could help the ramp pressure stripping, and that made them have a similar timescale. And previously we have only checked the most gas-rich galaxies, but with this model, we can actually extrapolate this into those with different initial H1 mass. These lines, they are hypothetical evolution lines for galaxies with different initial gas richness. And we can see that the stripping is actually, most of them are very effective only when they reach 0.5 R200. And with this, we get the depletion time scale here. Actually, this one is a bit different definition. We mean that the time between R200 till the gas is depleted. It can have different definition. If we, from more theoretical view, it is to 1 dex below the H1 mass main sequence, then they would follow the same. Most of them need about 1 giga-year. Only when initial gas is very poor, then it will be much shorter. But if we, from an observational point of view, for example, use some detection limit to define the depletion timescale, then the stellar mass would be very important when you define the depletion, the timescale. So possibly that's why this value could have a lot of difference between studies. So in summary, we use these 3 kind of parameters to study 2 kind of environment effects in NGC 4636 group. And we think that we successfully separate them, and we use them, we can estimate the depletion time scale and the stripping time scale. And for similar large-scale environmental effects on the molecular gas side, we could check the poster of Xuchen Li, and he's on the next half of the poster session, so you can hear his lightning talk on Thursday. And that's all. Thank you.
Questions?
Hi. When you model the ramp pressure stripping, how do you compute the gas density?
You mean the ICM density, right?
Yes.
We use the double beta profile from, we compile the double beta ICM model, X-ray model from about 5 different studies. Then we use the median one to match the total gas halo mass from X-ray observation.
So I actually had the same question, but maybe I'll ask another one. This tidal stripping is because of other satellite galaxies, other galaxies in the group. And you're just using the projected distance there, so you're ignoring any effect along the line of sight, is that right?
Yes, one of the caveats is that we only have the projected distance, but we estimated the error from this, they introduced the error from this error bar. It is from our estimation from mock data. We check how the projective effect would influence our measurement of this effect. So it is a quite large error bar, but the data dynamic range is also about 3 times, so the correlation is confident. But yes, there is a rather large scatter. Yeah.
Okay, and I guess all these galaxies are too mass. Sorry.
Sorry. And also we also include the tidal influence from very massive galaxy nearby, but not in this group. We also include them. Yeah.
Okay, and the tidal interaction with the, so the interaction with the tidal field of the group as a whole is not significant here? These galaxies are too massive, or?
Actually, because most of them are rather distant from the group center, so because the tidal interaction is inverse cubic with the distance, so in here we did not consider that yet, but we would like to take that into account into our future studies. Yeah. We propose to observe 4 more groups this year with FAST. We submit the proposal this year.
Okay, if there are no further questions before giving the mic to Bianca, let's thank who can and all the speakers in this afternoon. And also all the helpers that have been running around with the microphones.
Okay, just to say that we now move to the photo, to the conference photo, so follow me, and then you're free.